this video, we'll explain the concept of related rates as well as show some practical examples for better understanding. Hope you learn a lot. In many real-world applications, related quantities are changing with respect to time. For example, if we consider a balloon is being filled with air, both the radius of the balloon and the volume of the balloon are increasing. We can say that the rate of change of the volume V is related to a rate of change in the radius R. In this case, we say that dV dt and dr dt are related rates because V is related to R. When solving these problems, assign symbols to our variables involved in the problem. Draw a figure if applicable. State in terms of the variables the information that is given and the rate to be determined. Find an equation relating the variables introduced in step 1. Using the chain rule, differentiate both sides of the equation found in step 3 with respect to independent variable. This new equation will relate the derivatives. Substitute for all known values into the equation from step 4, then solve for the unknown rate of change. Water is being drained from a container which has the shape of an inverted right circular cone. The container has a radius of 2 inches at the top and a height of 5 inches. At the instant when the water in the container is 2 inches deep, the surface level is falling at a rate of 1.9 inches per second. Find the rate at which water is being drained from the container.
First, to solve this problem, we have to graph it. So we'll use a rectangle to do it, because the problem talks about a right triangular cone. The height of the cone is 5 inches, and the radius 2 inches. They also state that when the water is 2 inches deep, the rate at which the water is being drained is 1.9 inches cubed over seconds. Now we have to find an equation to relate the volume of the container and the water it holds. For this, we use the cone's volume formula, which is V equals 1/3 pi radius squared times height. But this is in terms of the cone, so we must change it to relate it to the water. We change the r for a smaller r, which represents the radius of the water, and the h for a smaller h, which represents the height of the water. The next step will be to relate the terms. In this case, we can say that the radius over the height of the cone is equal to the radius over the height of the volume of water. Then we solve for small r. Now, with the radius of the water, we can start doing the math. First, we plug r in and solve for that. We'll get a formula for the volume of water being drained. Lastly, we derive that equation and solve with the data we have. We'll plug in the 2 from how deep the water is and the rate at which the water drains. This will leave us with the total rate at which the water is being drained.
Suppose we have a triangle we know two sides of. This triangle has one side at 12 meters and another side at 15 meters. The angle between these two sides is increasing at a rate of 2 degrees per minute. How fast is the length of the third side increasing when the angle between the two sides is fixed at 60 degrees? Right off the bat, we already know we're going to be using the law of cosines. If you remember in trig, we learned that the law of cosines was the square of a side of a plane triangle, which equaled the sum of the squares of the remaining sides minus twice the product of those sides and the cosine of the angle between them. In this case, it's going to be totally applicable. Let's start off by converting what we do know into radians, because ultimately we're going to try to find the length of a side and degrees would not give us an exact value. Uppercase A equals 60 degrees. To convert this into radians, we multiply 60 degrees by pi over 180, giving us pi over 3. dA over dt equals 2 degrees per minute. If we do the same, we get pi over 90 radians per minute. Let's keep these values here on the side, so we're actually going to need them later. Now that we know uppercase A and dA over dt, we still need to find lowercase a. Let's plug in what we have from before to help us get A. We've got a squared equals b squared plus c squared minus 2 times 12 times 15 times cosine of A. Let's derive this equation with respect to time, and we should get 2a times dA over dt equals negative 2 times 12 times 15 times negative sine capital A times dA over dt. Now, all we need to do is just simplify this by isolating dA over dt, in which we should get dA over dt equals 12 times 15 times sine A over A times dA over dt. Remember, we still need to find A. To find lowercase a, we're going to have to find the square root of our filled law of cosines equation, giving us a equals square root of 12 squared plus 15 squared minus 2 times 12 times 15 times cosine of pi over 3, which equals to the square root of 189. Now that we finally know lowercase a, uppercase a, and also dA over dt, we can finally get the answer. Let's plug in everything into the derived equation we reached earlier. We should have dA over dt equals 12 meters times 15 meters times sine of pi over 3 over the square root of 189 meters times pi over 90 minutes, which equals the square root of 3 times pi over the square root of 189. And that's our final answer.